In sand casting, green sand is used for the making of moulds. Many metals can be cast, such as iron, shown here. Ingots or scrap, in this case old bottle moulds, can be used as the raw material for sand casting. The raw material is added to a preheated crucible with temperatures around 1500 degrees C. Once melted, the molten metal is poured into a smaller, preheated crucible. Impurities which rise to the top of the molten metal are scraped out and a degassing powder is added. The crucible and molten metal are then taken to be poured. The molten metal is carried in a small crucible to the mould. The crucible and molten metal weigh around 70 kilograms. The metal is then poured slowly into the mould. Steel plates and weights are placed on top of the sand mould to prevent the molten metal from pushing the mould apart as it fills the mould cavity. A cooling period of around 90 minutes is required for these large castings. Once cooled down, the mould is broken and the casting removed. These castings are of crosses to be used in a recently built monastery. A wooden pattern is used for the making of the mould. This is a split pattern. The finished casting will be made from aluminium. Here we can see the runner has been sawn away. The split line can also be seen. Notice the rough textured finish of the casting. The finished casting is cleaned and spray painted. To make the casting, one half of the pattern is placed into the drag of a moulding box. Fine used moulding sand is then sieved into the box and rammed tight using a dumper. Air holes are then introduced into the mould. The drag is now turned over, revealing the pattern. The other half of the split pattern is placed into the drag. Fresh green sand is then sprinkled over the mould surface. Parting powder is then sprinkled over the surface of the drag to further help prevent the two halves of the mould boxes sticking together. The position for the runner, or the pouring gate, is marked. The other half of the moulding box, the cope, is now added and sand is sieved and rammed into the cope. The cope is now removed. The runner is cut using a gate cutter. A steel tube is then used to cut the runner through the cope. The split pattern is then carefully removed from the mould. Loose sand is blown out of the mould using bellows. More parting powder is sprinkled over both cope and drag. The mould is now complete and ready for casting. A CNC milling machine is used to accurately cut 6 holes into an aluminium plate. The plate is secured onto the moving table of the milling machine. The guard doors are shut and the program is started. A cutting tool is selected from a rack and the plate is then moved into position. The cutting tool lowers and cuts the first of the holes. Cooling fluid is sprayed around the cutter to keep the plate and the cutter cool. This also helps in the removing of waste material from around the holes. The table moves, allowing the cutter to cut the next series of holes. The CNC milling machine can also be used to cut slots. Notice the marks left by the cutter at the bottom of the slot. Shapes can be cut from sheet steel using a punching machine. Shape tools are used to punch the material from the sheet. Here, the tool will punch out a circular hole. This tool allows for the punching of slots. sheet steel is placed onto the moving table of the punching machine and the program is started. The appropriate tool is selected and the sheet steel is moved into position. The sheet is moved, allowing for accurate cutting. Once complete, the sheet is removed. Here we can see that both circular and slot cutters have been used. Slots are to be punched into this aluminium handrail. The slots have already been punched in the rail on the left. The slots will be cut using the tools fitted to the power press. The punching tool will come down and punch the aluminium through the rectangular slot in the lower part of the tool. The rail is pushed into the power press. The guard comes down and the tool punches out the rectangular slot. The rail is removed and replaced to allow the other end to be punched. Here we see one of the punched slots. Notice the shear marks. This machine is a CNC brake press and is used here for the bending of sheet metal. Folding tools such as these are fitted to the machine. This sheet steel blank is to be folded to form part of a control box. The tool is set to 90 degrees. The guide stop is controlled by the computer. The machine allows for clean 90-degree bend. Here we see 2mm sheet steel about to be lifted onto the table of a laser cutter. The table is moved into the cutting compartment of the laser cutter. The laser moves on an overhead gantry above the steel. The position of the laser is controlled by the computer program. Here we see the laser cutting out parts for a hinge assembly. Notice the heat marks around the cut edges. Here we will see threads being cut into two holes of a steel mounting bracket. The bracket is held in the machine by the operator. Two rotating taps then cut the thread into the pre-punched hole. Thread is tested to ensure accuracy of fit. Here, small mounting brackets are being spot welded onto a motor shell. The bracket is placed in a holder above the shell. The guard comes down. The bracket is lowered onto the shell and spot welded. This operation is repeated for each of the 4 brackets. Notice the circular spot weld marks left on each of the brackets. This 100-ton press is being used to form a cylindrical motor shell from 2.5mm mild steel sheet. This is the final stage where the shell is being closed and the jigsaw ends come together. Here you can see how the jigsaw ends, punched from the original blank, help locate and lock the cylinder together. The cylinder is formed in a number of stages with a different tool being fitted to the press for each stage. The letters and numbers on these entry phone plates and buttons have been cut using both CNC and manual engraving machines. With the CNC engraver, the plate is fixed to a table and the cutting tool moves across the plate, cutting the letters according to the computer program. With the manual engraver, or pantograph, the button is held in a vice and the operator moves the cutting tool across the button. The number is cut as the operator traces its outline on a pre-cut plate. The arm connecting the tracing tool to the cutting tool gives a 1 in 10 reduction in size. This is 1/2 of a die used to produce an aluminium paint roller by pressure die casting. A releasing agent is first sprayed onto both halves of the die. The door is closed and the two halves of the die brought together. Molten aluminium is then ladled from the crucible into the ram chamber. The ram moves forward and forces the molten aluminium into the die. The paint roller is then removed from the die and checked. The excess aluminium from the injection point is removed for reuse and the paint roller is placed in the component bin. The operation is then repeated. Thin aluminium known as flash can be seen around the casting where the die has become worn and a good fit no longer exists. Here the split line can be seen indicating where the two halves of the die fit together. To remove the flash from the casting, a clipping machine is used. Here the paint roller is pushed through a clipping die tool. To give the casting a smooth finish, it is placed in a fettling machine. Here, ceramic chips and water smooth the paint roller as it is rotated in a drum. This automatic pressure die casting machine is being used to produce inner seals for a gearbox. Molten zinc is held in a heated crucible at one end of the machine. The molten zinc is then forced from the crucible by a ram into a two-part die. The die is then pulled apart and the ejector pins push the component out of the die into the cooling reservoir below. A moving conveyor belt collects the casting and transports it to the component basket for the operator to check. This casting shows two of the circular inner seals. Notice the three ejector pin marks. Here we see the two-part die with ejector pins. These moulds have been cast in aluminium and will be used in the production of vacuum-formed packaging. Air holes are drilled in the mould at points of maximum draw. Materials to be used come in either sheet or roll and in many thicknesses and colour. Here, the operator places a sheet of 1 mm thick polypropylene onto the top plate of the vacuum former. It is then clamped into position. Heating elements are then moved over the plastic sheet. Once at the correct temperature, the heaters are removed and the mould is brought up into contact with the plastic sheet. The air is then sucked out from beneath the mould, pulling the plastic sheet tightly to the mould. A cooling fan is then used to cool and set the formed plastic. The mould is lowered and the formed plastic removed from the vacuum former. The operation is repeated. Trimming of the excess plastic is done on a roller press. Here we see the dye used to make the lid of a container by injection moulding. The dye is manufactured by spark erosion. A graphite electrode in the shape of the dye is fitted above the fixing table. A steel dye blank is fitted to the magnetic fixing table. The sealed door is then closed and the chamber filled with a water solution. The electrode is then brought down to the steel blank and a 30 amp 90 volt current eats away at the steel. When complete, the electrode is raised and the solution is drained. This process leaves the shape of the electrode eaten away into the steel blank. Dyes can be manufactured for various shaped products, and they are available in many different sizes. Here we can see a range of dyes and their products. Recycled plastic can be used along with virgin material in the production of injection moulded products. Here we have polypropylene and white pigment used to give the plastic its colour. This blue pigment is added to polyethylene during the manufacture of these handles. Only 2% of pigment has been used here. The plastic and pigment are mixed together in a rotating drum. This mastic gun nozzle is manufactured using a mix of recycled sprue and virgin low-density polyethylene. Here we see polyethylene being sucked into the feed hopper of the injection moulding machine. It is then heated and injected by a ram into the dye. The dye is pulled apart and a robot arm removes the unwanted sprue for recycling. The nozzles are ejected from the dye by ejector pins. The dye closes and the cycle continues. The ejected nozzles are then transported to a collection drum on a conveyor. Timber is stacked waiting for the manufacture of spindles to begin. It is soon cut into blanks using a circular saw and a planer thicknesser. An automatic wood lathe with profile guide ensures that all the spindles are turned identical to each other. The cutting tool follows the movements of the profile guide. Here, the wood lathe is used to cut round end pins on a square section of timber. Pins are checked for a good fit after manufacture.